In this video, I want to talk about two important theorems. Rolle's theorem, which is important, and the mean value theorem, which is critical for everything that happens from now on. Let's begin with Rolle's theorem. Rolle's theorem, like most theorems, has the typical structure if, and then some conditions, which we call hypotheses, then conclusion. So if the conditions are true, then the conclusion must be true. So if f is a continuous function on the closed interval AB. So f is continuous. We can draw it without picking our pencil, chalk, whatever up from the writing surface between x equals a and x equals b. And f is differentiable on the open interval AB, this time with parentheses rather than brackets, and one more condition, f of b equals f of a. If those three conditions are true, then there exists, and you can use that backwards E symbol that I gave you at the beginning of the year for there exists an x value C somewhere between A and B, such that f prime of C equals 0. So if f is a continuous function on the interval AB, f is differentiable between A and B, and f of B equals f of A, then there exists an x value somewhere between A and B, such that the derivative of that x value is equal to 0. Hopefully that's sort of an intuitive statement. Let's take a look at a picture. Let's say we have a graph, y equals f of x, and here we have our x value a, and here we have our x value b. I want to try to visualize what each one of these things says. So I'm going to start with number 3 actually. F of b equals f of a. F of b and f of a, those are the y values at b and a respectively. So we're saying that we're at the same height at a as we are at b. So this height, I'll just pick a height, and that'll be f of b, and it will also be f of a. We're at the same height. So this thing goes through a point here, right at x equals a, and another point at the same height here. Hypothesis number 1 says I can start at this point and draw the curve without picking my chalk or pencil up from the paper. I can start at this dot and end at this dot without picking my chalk up from the paper or my pencil up from the paper. And remember what differentiable means. Differentiable means has a derivative, but we came up with an intuitive word for that. We said differentiable means smooth. So if I can draw a smooth curve between here and here, what this says is there's some point where the derivative equals 0. Let me just sketch in any old curve. I'll just draw something like that. You can see in this picture, there are a couple points where the derivative equals 0. I could have picked the point right at the top of this hill. I could have picked C right there, and you can see the derivative at the top of that hill is 0, because we know that if we have a local max, a relative max, or a relative min, the derivative at that relative max or that relative min is equal to 0. I could have also put C over here. I didn't, but I could have. All this says is there exists at least one point between x equals a and x equals b where the derivative equals 0. This one happens to have a couple of them. You could have 100. You could have infinitely many, but there's at least one. I think you can see that if you can draw a point from here to here, there's either going to be a top of a hill or a bottom of a valley or both, or maybe it's just a horizontal line, but no matter how you slice it, there's going to be, since the curve is nice and smooth, at one of those tops of hills or bottoms of the valley or anywhere you want along a horizontal line, the derivative is going to be 0 because it's going to be horizontal there. The tangent line is going to be horizontal. The formal proof of this is in your textbook in section 3.2. I'm going to omit it today in order to keep things short, but I want you to know that the proof uses the extreme value theorem. So we use the extreme value theorem as part of the proof. Now I want to move on to the mean value theorem. I'm going to leave the extreme value theorem up for comparison's sake. The mean value theorem, you can probably guess we abbreviate MVT, just like we abbreviate the intermediate value theorem IVT and the extreme value theorem EVT. We use the EVT to prove this. So the mean value theorem, if f is a continuous function, on the closed interval AB. So that should look awfully familiar so far. And secondly, this will give you a feeling of deja vu again. F is continuous on the open interval AB. So far, this looks exactly like Rolle's theorem. But in Rolle's theorem, we had this third condition. This time, we're going to drop it. I think you can see if we don't demand that these 2 points are at the same height, we may not have a place where the derivative equals 0. So the conclusion can clearly not be the same. Then there exists an x value c somewhere between a and b, such that f prime of c, the derivative of c, might not be 0. There might not be any places where the derivative is 0, but the derivative at c is equal to f of b minus f of a over b minus a. So since the 2 points at the ends are not at the same height as they are over here, it may not be the case that there's a place where the derivative equals 0, but we can conclude this, that there exists a point at x value c where f prime of c equals f of b minus f of a over b minus a. And I want to draw you a picture here too. So here we are at A, here we are at B, and these 2 points might not be at the same height. The value on the curve at these 2 points might not be at the same height. So let's put f of A right there. We'll put it at that height. And let's put f of B at a different height. They could be at the same height, but probably not. So here's f of B. And hypothesis 1 says I can draw a curve between here and here without picking my chalk or pencil up from the writing surface. And 2 says, oops, sorry, that shouldn't say continuous, that should say differentiable. Sorry about that. Differentiable, just like it does over here on the open interval AB. So that says I can do it smoothly. I can draw a smooth curve between this height and this height. Let me go ahead and do that. I'm just going to draw in any old curve. Now, f of b minus f of a, that's this distance between, we go between a and b, between these two y values, divided by b minus a, that's rise over run. F of b minus f of a, that's just the slope of the line connecting these two endpoints. Let me put this, actually. So the slope of that equals f of b minus f of a over b minus a. That is just the slope of the secant line connecting these two endpoints. And all this says is that there is some point between a and b where the tangent line is parallel to this line. So let's see, it's too steep here, too steep, too steep, too steep, right about there, right about at that point, there is a point where the tangent line to the curve is parallel to this given line. I don't know if I've drawn that so it's parallel. And on my picture, there's another point where it's parallel. So I could put C right here if I wanted, or I could put it, let's see, right about here, I guess. There's another point where the tangent line to the curve is parallel to the secant line. That's supposed to be parallel again. I don't know if it looks parallel. So this point, this line is parallel to this line. So C could be over here. I could have just as easily put it over here. But this says there is at least one. There's at least one. And now that I've corrected the word continuous to the word differentiable, that should say differentiable in your notes. These two are identical in hypothesis 1 and hypothesis 2. The mean value theorem is missing hypothesis 3, which was sort of unnatural anyway. And we had to have a slightly different conclusion. And let me talk to you about two things. I'm going to get rid of Rolle's theorem. I said that we used the extreme value theorem to prove Rolle's theorem. If you recall, when we did the extreme value theorem, we didn't prove it. We have no idea how to prove the extreme value theorem. If you want to prove the extreme value theorem, you'll have to take some more math courses, and eventually we'll learn enough about the real numbers to be able to prove the extreme value theorem. But in this course, it's a little bit beyond our scope at the moment. So we use the extreme value theorem to prove Rolle's theorem. Rolle's theorem is used to prove the mean value theorem. You basically take the original function and subtract off a line like this, and that sort of makes everything horizontal again, and then you just apply Rolle's theorem. I'm not going to go through the details of that right now, but the details are in your textbook. We also have no idea, just as we're talking about it, how to prove the intermediate value theorem. So I would say of the big four theorems in Calculus 1, we have now seen 3 of them. The big four, well, the big 3 so far are the extreme value theorem, the intermediate value theorem, the mean value theorem, and we have one more, which has a very impressive sounding name, called the fundamental theorem of calculus. And we're going to use the mean value theorem to prove it. But right now, the mean value theorem is sort of built on top of Rolle's theorem. It's like this is a floor of a building, and it's built on top of that. And this is built on top of that. And we're actually not sure what's holding this one up. That should bother you a little bit. We also don't know what's holding this up. The other thing I want to talk to you about is what the purpose of the mean value theorem is. I just want to spend a moment on this. The point of the mean value theorem is that it allows us to take information about the derivative about f prime and draw conclusions about the original function. Up till now, we've taken the original function and computed the derivative. And we've done things with the derivative. But what we're going to do following this is take the derivative and then use the derivative to draw conclusions about the original function.